Hi there, welcome back. So we spent a lot of time in Chapter 4 building some background knowledge for what it is that we're talking about. We talked about forces, we gave an introduction into Newton's laws, we talked about free body diagrams. We did all this different stuff to set up stuff to get ready to solve it quantitatively. So that's exactly what we're going to do is we're going to get quantitative with things. So part 2, this next part of our unit 2, is going to do just that. We're going to start taking a look at how we can solve these problems quantitatively, getting a little bit more of information in there and going from there. So the first part of this chapter, there is a pre-lecture video on static and dynamic equilibrium. And we'll talk about exactly what that means, but essentially this is going to lead us into how we quantify any problems dealing with Newton's first law. Okay, so we're going to start this by taking a look at our first pre-lecture video. And in this pre-lecture video, he introduces the concept of static and dynamic equilibrium. Equilibrium, of course, meaning balanced. So if I were to imagine a free body diagram, let's say of moving a box across the floor, I know that I have a weight force, a normal force, there's a force of a push, and let's say I'm pushing it across the floor at constant speed. That would give me some kinetic friction. And we've talked about this exact thing before, but this is in equilibrium because all of the forces are balanced. But the point in the pre-lecture video is there are two types of equilibrium. This example right here is dynamic equilibrium, meaning that it's in motion. The forces are balanced and the acceleration is zero. And as we know, any object in motion tends to stay in motion unless there's an outside force that acts upon it. So this one is in equilibrium and it's balanced at zero. But now what would happen if I just, instead of kinetic friction, let's say that I had static friction. Well, now the forces are balanced and the acceleration is still zero, but the object is not moving. And that brings us to the concept of static equilibrium. Static equilibrium means that the object is stationary. So we'll address both of these as they pertain to Newton's first law in this section. So our first section in chapter 5 is all about Newton's first law. So you just watch a pre-lecture video talking about static and dynamic equilibrium, and now we're going to get a little quantitative and look at some problems with them. So equilibrium, by definition, is anything that's balanced out. So in physics class, we will have an object that is at rest, in which case that means it's static equilibrium. So the forces are balanced out, but it's stationary. But we can also have an object moving in a straight line at a constant speed, and that'll be dynamic equilibrium. In both of these cases, there is no net force acting on an object, and the acceleration is zero, but that doesn't mean there are no forces acting on the object. It just means that the object is not accelerating, because as we've talked about over and over again, forces cause acceleration. So I do have a couple formulas for this. The sum of the forces in the x direction equals mass times acceleration. That's from Newton's second law, and that equals zero because there is no acceleration. And the sum of the forces in the y direction, same thing, also equals zero. So this little weird looking E here, for those of you who aren't familiar with it, this is sigma. And sigma means the sum of all the forces. So the sum of all the forces equals the first force plus the second force plus the third force, etc. As we look in each direction, both the x direction and the y direction. We evaluate those independently of one another. So let's go ahead and jump right into an example problem. We have an orangutan weighing 500 newtons, hangs from a vertical rope. What's the tension in the rope? Well, if he's just hanging there, this is an equilibrium problem. So I can simplify it by drawing a free body diagram. I know that there's a weight force going down, and that weight force is equal to 500 newtons. And there's some tension force going up. Now, take a second and pause and just think about, if you can think about it just with common sense, what is the value of this tension force? So pause the video, take a second to think about it. So many of you instantly thought, hey, that value's got to be 500 newtons. And that is correct. But obviously all of our problems aren't going to be this easy. So let's take a look at it, how we would set that up quantitatively. So we know that this is all happening in the y direction. So that means that the sum of the forces in the y direction equals mass times acceleration in the y direction, and that's going to equal 0. So when I mean the sum of the forces, I add up all the forces. And the sum of the forces, so there's forces in the positive direction, and that's going to be tension. And there's forces in the negative direction, and that's going to be weight. But in equilibrium, the acceleration is 0, therefore the sum of the forces is 0. And I can say that therefore the tension is equal and opposite to the weight. The tension is 500 newtons, so the weight must also be 500 newtons. I'm sorry, the weight is 500 newtons, so the tension must also be 500 newtons. So how I solve this problem is I said the sum of the forces in the y direction equals the mass times the acceleration in the y direction, and since it's in equilibrium, they equal 0. I added up all the forces in the y direction. The tension force, that is going in the positive direction, and the weight force, that is going in the negative direction, hence why I put that little negative sign there. I can also have multiple forces going in each direction, and I would add them all up, and we'll see that more later. Then I said that therefore that the two of them are in fact equal to each other, and therefore if my tension or if my weight is 500 newtons, then so must my tension. Here's just a quick little better picture or visual of the problem. And we know that the net force is 0 from that. So an orangutan is hanging, and we know the net force is 0. Here's, again, the free body diagram. And just like I did, we add up all the forces. You'll see that they did, in this example, there's a plus sign. That's true. The weight, again, is in the negative direction, so therefore I know that it is subtracted. And we can see that right here, they did a subtraction sign and said that that must be negative, but they're equal and opposite, so the tension has to be 500 newtons. So this is just a quick conceptual example. We said that the conceptual example is a rod is free to slide on frictionless sheet of ice. One end of the rod is lifted by the string. If the rod is at rest, which diagram shows the correct angle of the string? And this is a frictionless surface, which means that I can't rely on friction to counteract the forces. So the best way that I can evaluate this is by taking a quick look at the free body diagrams. So here are the free body diagrams. For scenario A, we look at, and it's right there. So we have a tension going off and to the left. We have a normal force from the surface going up. And of course, we have the weight force of the object going down. According to my free body diagram, I have a net force right there. And B, I have the weight force going down. I have a tension force going up and a normal force going up. And these two, those are actually all balance. So B is actually my correct answer. And C, same thing, tension going off to the side. That's going to cause me to have a net force going off to the right. So C can't be the right answer. So by looking at all of them, we want to look and see when the net force is 0. And that is when the tension is straight up and the weight is straight down. Another quick example for you. A car with a mass of 1,500 kilograms is being towed at a steady speed by a rope held at a 20-degree angle from the horizontal. So here's what I said before. These will start to get tricky because now we can start having forces being pulled at angles, and that'll make things a little bit more complex than we were used to, with just having straight in the x direction or straight in the y direction. But I solved the problem the same way, actually. So I'm going to start by drawing a picture of this object. And by me, I mean I'm going to use the picture that I already have. Hey, look, that was easy. So there's my picture of the object right on the left-hand side over here. And then on the right-hand side, I do have a free body diagram. And in that free body diagram, I see that this tension here, that's actually really important, is at that angle. So when I'm looking for the tension, I have to ask myself the question, what is tension? Well, tension is the force exerted on the rope. Where is that tension coming from? Some of you might ask that in your relationships. And the tension is counteracting friction, but the interesting thing is you're also pulling up on the car. So some of the tension is combining with the normal force to counter out the weight. This gets really confusing. Why is it confusing? Because this tension has an X component and a Y component. It's acting in both directions, hence that little that theta there, it's acting at an angle. Okay, so it's kind of weird, but I think I kind of got an idea, right? There's an X component of tension, and that's balancing out the friction force. There's a Y component of tension, and that's balancing out some of the weight in addition to the normal force. It's confusing. You have to be able to visualize the forces that are acting. And then I can say, all right, if it's going at a steady speed, which indeed it is, that means all of the forces must be balanced. So let me go ahead and go to the, say, well, we start with the sum of the forces in the X direction, that equals 0, and the sum of the forces in the Y direction also equals 0. So let's see what those statements look like on the next slide. So here is my sum of the forces in the Y direction, here is my sum of the forces in the X direction. And like I talked about before, in the Y direction, there's a normal force, there's a tension. There is no frictional force, but there is a weight force. And that all has to equal 0. In the X direction, looking at all the forces, there's a normal force. Oh, wait, nope, definitely not. No normal force in the X direction. There is tension, there is friction. Is there weight? No, there's no weight in the X direction. We're not on a hill. Okay, so I'm actually going through and taking a look at all of my forces and thinking what direction they act in. And when I do that, now I can actually go to that, and now I see the correct formula. So thinking about what forces are acting, that's going to help us solve this problem. But I know that each direction, they equal 0. So I can sub in and figure out exactly where my friction is. So here are my expressions for each direction. In the Y direction, I have the normal force going up, and I have a Y component of tension. Those are both positive, and then I have the weight force going down, that is negative. In the X direction, I have the X component of the weight, the X component of the tension to the right, and then friction to the left. Now, if I'm solving for tension, I can actually use either one of these formulas to figure it out. But since we were given this force of friction, I know that in the X direction then, T cosine theta, the tension, has to be equal and opposite to that 320 newtons. So I can use that to solve for the actual tension of this problem, and I'll do that right now. So the actual component of tension then is the force of friction divided by cosine theta. Friction was 320 newtons divided by the cosine of 20 degrees, and I get an actual tension of 340 newtons. Again, these problems can get very tricky, so I need to make sure I'm keeping track of all of my forces, and I do that with this nicely made free body diagram, and I know that the net force is 0. This is just one more little thinking about tension and how the tension is actually, like I said before, taking away from some of the normal force, because these two have to add together to equal out the weight. And one last little quick check. We have a ring as seen from above as being pulled by three forces. It's not moving. What's the force of this big F right here? That big F needs to cancel out each of these forces. And these forces are applied both in the X direction and in the Y direction. So therefore, I know that it has to cancel out definitely the Y direction, but these two actually right here, these X directions, cancel each other out. So really, all I care about is the Y component in each, which is going to be 10 sine theta. And if I cancel out both of them, I need to get a total force of 20 sine theta. So again, this is a very tricky section, and we'll be spending a lot of time practicing problems from this as we go through this chapter. So if you're overwhelmed, make sure you take a look at a couple of the problems, and we'll take a look at those in class.